Okay, so again, just a heads up, this is the last week of stuff before the midterm. Okay, so the homework, I tried to make it shorter this time. So hopefully it seems shorter. We cut out a couple of the sections, which I think will be helpful. So on Saturday or Sunday one, there'll be a video that's a review kind of everything that's going to be on the exam. And then on Thursday, so a week from today, we'll have just a review session that you can ask whatever questions you want to ask, and I'll answer those. And then I'll probably, and I haven't heard anybody have an issue with this, I'll probably release the exam on Friday, and you can take it anytime until Sunday. Okay. And once you start, I'll make it a 1 hour exam, but I'll probably give you 2 hours. So in my mind, it's a 1 hour exam, but my mind and your mind may not be the same thing. It's, I mean, you guys know from teaching, it's hard to know how long it's going to take students to do things. I mean, so if I double it, then we should be okay, I'm hoping. So hopefully that'll be good. So what questions did you have about this chapter?
It's been a while since I've done the matrix, what's the word? Matrix stuff, math, math things. Yeah. So the Gaussian elimination, that is just basic like matrix simplification or whatever. I don't know what the right word is. It's been forever since I took the linear algebra stuff.
Yeah, me too.
But I mean, it's not anything special. It's just getting the ones across the diagonal. So by like flipping things and whatever.
Well, you're going for zeros instead of one. So you're going for zeros if it's a three equations, 3 variables. Mm-hmm. So you have 4 columns. So you include what's over on their side of the equal. You want to have 3 zeros at the bottom. So at the end.
But ones across the diagonal, right?
You don't care about, no, you don't care about ones at all.
Oh, okay.
All you need, so on that bottom row, you need to have it in terms of one variable in essence. So if you have X, Y, Z, you want to have 0, 0, something, something. So then right. You can say that if you have a 3 and a 5, well then 3x equal 5. And then you can use that to solve the one above it, and then that to solve the one. And I put out a separate video that I'd done, I think a year or so ago, on the Gaussian elimination, just so you can follow through that in a little more detail than I did on the other video. But yeah, with that, you're transforming the equations into a coefficient matrix, and then you're just transforming that into this special form. It's if you solve systems of linear equations, again, it may be been a while since you've done that. This is doing the same thing in a more straightforward may be the wrong word, a simpler way.
Okay.
It's theoretically more remote maybe than doing it the other way, but it does save you a lot of time. And I didn't ever see that until I took an algorithms class. I don't know why they don't teach that when you're learning that in school, because it seems like we did that in high school, systems of linear equations, but I don't.
You do systems of equations in algebra and algebra 2.
Yeah. So why
but it's usually 2 and, no more than 2.
Right. So maybe they don't have the matrix math for it. I don't know. I don't know why they don't.
No, they do substitution and elimination and graphing.
Right. I mean, that makes sense, but it just seems like somewhere. I mean, I had a degree in math and didn't see it at all. I took linear algebra, didn't see it at all. We did eigenvalues and eigenvectors, but we didn't do this thing. As far as I know, maybe I still remember. But yeah, when I saw it in the algorithms class, I'm like, whoa, this is kind of cool. So.
I was really glad you put that extra video out. It helped immensely.
Yeah, I didn't do more in the video because I knew I'd done that before, and it needs its own video that just goes through step by step. That's the kind of thing, if you've got it, it's stupid simple. But if you don't got it, it's impossible, and it's like I'm speaking a foreign language. So yeah, because it's not, I don't think it's very intuitive. I mean,
I couldn't figure out from the book, like there wasn't enough explanation in the book as to what like they were actually doing with the numbers, and so having you walk through it was incredibly helpful.
Well, yeah, at the end it's like, you've done this, now you're done, here are the answers, and you're like, where did that come from? Yeah, I mean, yeah, that makes sense. So yeah, most students, once they figure it out, they're fine, but it can be a little confusing to get that going. Okay.
Do we need all the stuff in section 6.2 on LU decomposition
Nope.
and matrix, inverse, and
Nope.
determinant? Okay.
No,
didn't
I
think
said
so.
that specifically in the video that all
Okay.
I care about.
I haven't quite caught up on the video yet.
Gotcha. Yeah, well, this will be interesting because there's a lot we're not covering in this chapter. And that's the first thing that we're not covering.
Yeah, I barely got through reading those sections. I just haven't quite gotten through the video yet.
Gotcha.
Can I ask a question about 6.1? And it's
Yes.
on the time efficiencies, which is something I'm starting to come around to, but still a little fuzzy on.
Okay.
So the second part of the question asks you to compare the pre-sorting with the brute force and the divide and conquer.
Yes.
And in the back of the book, it says, which I know the brute force is linear because
Yes.
you're comparing each one at a time,
Yes.
is linear time. But it also says like the divide and conquer is linear time.
Right.
And I don't understand that because I thought most of the sorting algorithms, are they in log m because you're dividing it?
No, there's a lot more work to do on sorting. When you're looking for the biggest and the smallest, there's just really not much there to do. And
Okay.
and that particular problem doesn't really suit itself well to a divide and conquer. I mean, you can divide it in half and find the smallest of the first group and the smallest of the second group and compare those, but it doesn't help you out that much. It seems like kind of like merge sorts. I mean, you may be thinking, well, why doesn't that work better? Well, and the reason being that we're with a sort, you have a lot more mixing around of the elements. So the divide and conquer makes sense. Okay, but it's still more than linear. So again, n log n is bigger than n, right? Because you're multiplying by log n, and log n is smaller than n, but n log n is bigger than n. Okay, so that's what people get confused on. I think Anna had a question on the forum about this, that with pre-sorting, well, why even talk about it if it doesn't make it any better? Well, and it varies. I mean, my answer on the forum, if you haven't seen that, is basically, if you're solving a problem without pre-sorting, just taking it what you've got, okay, and you can solve that problem in linear time or better, so linear or logarithmic or constant, then doing the pre-sorting is not going to help you at all, because pre-sorting, you have to assume you're going to have an n log n. Okay, so it's only, and even if it's equal to n log n without pre-sorting, it wouldn't make any sense to do the extra step of pre-sorting. Okay, so when you're looking for algorithms that have the possibility of benefiting from pre-sorting, they've got to be n squared or above, right? So a good example of when you would pre-sort would be when you're looking for distinct elements in a set or in a list, okay? Because if you sort them, they'll be right next to each other, and you drop from a n squared all the way down to an n log n. So that's worth doing.
So David, just a general question. Like if you look at the chart that is on page whatever, 59, like in chapter 2.
Okay. Yes.
The time efficiency gets worse as you go down the list, right?
Yes, because the best is constant, the worst is exponential or factorial.
Okay. So why is divide and conquer linear time? Because if you're dividing and conquering it, you're not like you're dividing by 2, right?
Right, but you're not reducing the problem by 2. If you have 10 elements in a set, you're looking for the biggest and the smallest.
Right.
What we wanted to divide and conquer is you can divide it in half and get rid of half, like on a binary search if it's sorted. But if you're looking for the biggest and the smallest, you still have to look over here and over here. You haven't reduced the problem any. And that's why it's so linear. It does you no good at all.
Okay.
Does that make sense?
So yes. So on the sorting, it is an n log n because you're I don't understand that. Sorry, I must be like missing the point completely.
No, it's the log n comes from the fact that you're able to reduce the problem in half, divide it up, but you still have to deal with it. So that's where you get the n log n. If it's something like a binary search, it's just a log in, right? It's
Okay.
better than in. So logarithmic is better than linear, okay? But the sort, you can't just divide it in half and forget about it. So that's why it's at the end log n.
Because you literally have to look at each element. That's why
Yes.
because you would be looking at every element anyway.
Yes, everything has to
Okay.
be touched to do a sort, but the rearranging you can do in log n if you're doing divide and conquer, but you still have to touch everyone.
Okay. Okay. So on that one, because the question is which is fast, or I guess like, does it make a difference?
Right.
So no, the pre-sorting doesn't do you any good because
No.
that's in login time.
Yep. Pre-sorting makes it
And-
worse.
Okay.
Yep. That's the answer there. The pre-sorting makes it worse.
And I'm still really hazy on the time efficiency, which is why I don't know. I mean, I can do the little Gaussian thing, but the time efficiency is killing me.
They're hard to get ahead. Some are easy and some are not. So.
And I had a question on like the Gaussian elimination.
Yep.
So do you always use row 2 or you use row 1 to eliminate row 2 and then you use
Nope. You have no such boundaries. In fact,
Okay.
you can rearrange the order of the rows if you want. There's
to
nothing
make
special.
it easier to manipulate?
Yeah, so if you already have one that's only in 2 variables, you can put it at the bottom, or you can do whatever you want. So row 1, row 2, I mean, because when you have a system of linear equations, it's a set, there's no order there, okay? So you can move it however you want. Then when you're changing it, you can either add or subtract a multiple of any other row. Okay, so it doesn't matter. In the examples, they tend to have a 1 in the top row, so 1's a good one to makes it easy to, you don't have weird numbers when you're multiplying them out. But yeah, no, you don't have to use any particular row.
Well, and I guess that's my question. Like if we get one of these on the midterm,
Mhm.
like are they going to be numbers that are fairly easy to deal with?
I'm
Are
going to
they-
try for it to be easy numbers to deal with. I may not succeed, but that will be the effort. I will
Because
try
I
to
mean,
make it.
I understand it on a surface level, but I'm not sure if I got really down deep in the numbers that I could
Mhm.
make it all work.
But just think you're taking a row and then you're either adding or subtracting a multiple of some other row, okay? With the
Mhm.
goal being you want to wipe out, you want a 0 in that first column the first time, and then for the last one, you want a 0 in the second column as well,
Mhm.
okay? And
I was working on, sorry,
go ahead.
I was going to say when I was working on that one last night, I worked on it a really long time. And at first I thought based on the book one that you had to do it a certain way.
Mhm.
Like you said that you could do it any which way, like
Yes.
compare them anyway to get to the
Yep.
0.
Yep.
And so when I went and I thought I was doing it all right and I plugged the numbers back in and they didn't work. And so,
I hate when
and
that
I guess I was thinking about it in my sleep or something because I woke up still thinking about that problem.
That's what
I
math
had to do
does.
this
It gets in
morning
your
to
head.
figure it out for peace of mind.
Yeah, in fact, you can do whatever row you want. I mean, it just depending on how you put them together, you can use, if you're doing row 2, you can use row 1 or row 3. And while the intermediate steps will be different, the end result's going to be the same. Okay. The
Yeah, I
x1,
think
x2,
like
x3 equal what they equal. And that's like if you have an equation, as long as you do the same thing to both sides of the equal sign, it doesn't matter what you do. There's more than one way to solve it. So it's more of a technique than it is a very prescriptive kind of thing.
Yeah, I didn't like how the book example tried to make it like it had to be a fraction, and that was
Yes.
what was throwing me off. And then,
Yeah.
then when I watched your other video and you did a plus instead of a minus, and then I was like,
Yes.
oh, you can just compare it however you
Yes.
compare. Okay.
Now,
Yeah,
that
I couldn't
helped a lot
figure out
better.
the fractions in the book either. That's what threw me. I couldn't figure out what they were actually doing.
Well, the reason they do that, if you look at programming this rather than solving it by hand, you can't do what you're doing in your head, right? You have to create that fraction. That fraction is going to, you have to make sure that you're getting, the things that are going to cancel out. So that's why it does it. It does it to show you this is how you would calculate this. We just do it in our heads. But for an algorithm, for a computer program, it would have to actually create that fraction because each of the numerator and denominator mean things from the problem. I mean, you pull those out of the problem. So yeah, I see why they do it that way, but it does add to the confusion when you do them by hand for sure.
Yeah, but the way that ours is, so for example, like from the first one, when you're doing the row 2 to get it to the 0, it's like row 2. The way I did it was like row 2 minus 2 times row 1, which if you did the fraction, would be like 2 over 1, but I just put 2 instead.
Yeah, it's the same thing. Yeah. Or they'll have
And
4
then
over 2 instead of 2.
Easier on the brain.
Yeah, I agree.
Yeah.
Other questions on Gaussian, just how it works, why it works. I'm not sure I know the whys exactly, but what we're trying to do with it. And again, it's easier for me to substitute in X, Y's, and Z's instead of X1, X2's. But for the algorithm, you need those numbers because you can't know, the algorithm can't go up by 1 from X to Y as easily as we can. So, yep. So other questions on, I guess that's section 6.2. That just had the Gaussian, that was all, wasn't it?
Yeah.
Okay. Okay, 6.3 on the AVL trees.
I didn't understand the, sorry. I didn't understand the, on page 219, the figure 6.2 where it talks about this one is an AVL tree and this one is not. I wasn't quite sure I understood the definition, I guess.
Okay. I'm getting there.
I didn't understand, Kim, like how they were getting those differences. And like on the 0, the 1, the -1, I couldn't figure out where those were coming from. And
Yeah.
found
Like
a video that explained like how you do those balance factors.
Yeah,
or whatever
it's
called.
for each one. So if it's a leaf node, it has no children, then it's 0, right? Because it's balanced. It has this, what that number represents is the same number of left children and right children.
Okay.
Okay. So when we go from so 2 and 8 both have 0s. When we go here to 4, okay, we're going to take the left children, which is 1, minus the right children, which is 0. So it's a 1.
Okay.
Okay. Over here, we have the left children, which is 0, minus 1. So that's why that's a -1.
Okay.
This one, since we have these already, we don't have to worry about calculating the rest. This is just a 1 minus 1, or it's a 0. Okay. And this one is, so over here, this one's a 1 because there's a left child but no right child. So that's a 1. Okay. So this has a 0 and a 1. So it's a 1. Okay.
But why, so why is the top a 1? Because didn't you say you were subtracting? So why isn't that a -1?
That should be a -1. Yeah, that should be a -1. Yeah. I hadn't thought that, but yes, it should be, this is a 0 minus 1. It should be a 1. Yep.
So then on the one next to it, why is that one a 2?
That's not correct. That's not correct.
I was gonna say, is it
It's-
right minus left, or is it left minus right?
But it's not just the ones, you can't look at just the ones below it. This is a 1, 2, 3 is the maximum over here,
That's right.
minus 2. That's why it's a 1. So you can't just look at those. Okay. So this is not a 1 minus 1. It's a 2 minus 2. So you have to keep calculating the children factors. That was my mistake. That's why that's a 1. Does that make sense,
Does it
Cam? You still look
matter how you-
confused?
I'm still not seeing the numbers for the top.
So 10 on the left side, the levels of, or the height of the left subtree basically
Okay.
is 1, 2, 3. You
Oh, and the other one's
subtract
only one.
the 1,
no.
2. So 3
Oh,
minus
okay.
2 is 1. Okay.
Okay.
So over here, you've got 1, 2, 3 minus 1,
Okay.
which is 2. 2 violates the AVL tree.
Got it.
Has to be
Okay.
a 0, 1, or -1. Okay.
That makes sense. So on the problem, they want us to kind of like figure out those numbers, and so we
Yes.
can look at that and figure that out.
There's a trick question there though, but I got wrong till I checked with my answer guide. They also have to be binary trees. So don't forget to check that they're binary trees, which means every left child is greater than the root, and every right child is bigger. Sorry, every left child's less than the root, and every right child's bigger than the root. So if the tree is
Okay.
otherwise balanced, it's still not going to be a AVL, because AVL.
Well, it says which of the following binary trees.
Yes, they're still binary because they have 2 children, but they're not a binary search tree unless they have the property that all children to the left are less than and all children to the right are greater than the parent.
Oh. Okay.
Okay.
David, does it matter how you subtract them? Like, do you always subtract the left from the right, or is it right from left, or does it matter?
It's left from right, but as long as you're consistent, it doesn't matter.
Okay.
There's no practical difference.
It just changes the sign, which I
Yes.
don't guess it really matters.
Nope. Left minus right is the official way that it's defined, but it doesn't matter. As long as you're consistent.
And then for number 2, part A, where it says to draw all the trees for these different amounts of nodes.
Yep.
Then are the nodes considered the leaves, or like each little circle?
The node's a circle, yes.
Okay,
So how many graphs
So-
can have only one circle? Only one.
right.
But 2, there could be 2, right? There could be 1 with a left child, 1 with a right child. So there
Okay.
are 2 at 2. Okay.
So those are considered different?
Yes.
Okay.
Yeah. So there are 2 with 2.
And they have to be ABL. Okay,
Yes.
seems straightforward enough.
And again, on the rotations, I think that's interesting, but it's kind of beyond what we're doing here. So I'm not going to ask you that on a test situation. Okay. But I mean, you should know, you should be able to recognize an AVL tree, and you should know why we do AVL trees. Okay. And the idea is that they're self-balancing, because a binary search tree in the best case is logarithmic, because you immediately, if you're looking for something in a binary search tree, if you go to the root, if it's
We're
balanced,
splitting.
you're getting rid of half. Okay. But if you add the numbers 1 through 10 sequentially, you don't get a tree, you get a stick. Okay. And you're still at linear. So the worst case is linear. So it's in your interest from an efficiency standpoint to have a balanced tree. And the idea behind an AVL tree is that it's easier to balance a tree while you're adding a new element, rather than going on at some point in the future and having to rebalance everything. So they maintain self-balancing. Okay. And then the other things from that chapter are the 2-3 trees, which just allow there to be up to 3 pieces of information per node temporarily, to avoid having to do the rotations. Okay, so that's the difference there. Okay. Other questions on the AVL trees?
Once I figured out like how they got those numbers, it was pretty straightforward.
Yeah, it's not bad.
I feel like I just have a hard time reading math.
Yeah.
Like I've just,
It's a skill that you get rusty on.
it's hard,
Yep, that's for sure.
which is all of our students' problems too.
Yep. Heaps and
On
heap
that-
sort.
On the, going back to the AVL trees there.
Okay.
In the homework,
Yep.
that middle one. The question B there, it's
Yes.
throwing me off. It's not a binary tree because of the 4 and the 6 all by themselves, right?
No, the 4 and 6 are okay. Because it's smaller to the left and bigger to the right.
All right, I'm gonna have to think about that one.
And again, you start at the bottom and look at every one. So the 1, 3, the 7, the 9, all are zeros. The 2 and the 8 are also zeros. Okay. The 4 is 2 over here and none over here. Okay. So yeah, we're in violation right now. Is that what, that's not what you were asking though, was it? Or,
Yes, that's what I was confused.
oh, I
about.
thought you were saying because you thought the 4 was out of order and it wasn't a binary
No,
search.
no, not out of order, just, it doesn't have right
Yes.
child, so.
Then you are correct. Yeah, I
It
thought you were
messes
saying
it
it was
up.
something, because we'll go ahead and we'll spill the beans here. When I
Okay.
looked at this one, C, I thought, oh, C is an ABL tree, right? But it's not.
Because of the right side.
The 7.
Yes. No, the 7's okay. No, what's not okay?
The
Something's not
7
okay.
and the 2.
Seven's
No.
not okay and the 2's not okay.
The 2.
Oh, right, that's
yeah.
correct.
Oh,
Yes.
2.
The 7's on
Yeah.
the right side of 5, but it's on the wrong side of 6.
Mhm.
Yeah.
And the 2's on the wrong side of the 3, right?
Yes. Yes, that's correct. So that's a tricky question that I got wrong. That I wouldn't
So
ask
we're
on a test because that's just me.
So that one's that's the one you were saying is not binary? No, not binary.
It's not a binary search tree. It is a binary tree. It has no more than 2 children. But in a binary
why is
search
it-
tree, everything to the left is smaller, everything to the right's bigger.
Oh, okay.
So 2 is not bigger than 3, and 7's not smaller than 6. So that
Got
was a
it.
trick question. Okay. Anything else on ABLs? Okay, so let's talk about heaps and heap sorts. Okay, so heaps are interesting, and it to me reminds me of doing the partitions, that you're kind of semi-sorting something, okay, but not exactly. Okay.
Is a
And
heap supposed to be like a tree? Like,
it can be. You can either work with it as a tree or as an array. For me,
because like
practically
I feel like
solving
a lot
problems-
of these things we've seen before, but this one we haven't. Like in the data structures,
right.
is it considered a data structure?
It
I'm
is.
assuming?
Yes.
Okay.
I'm surprised you didn't see a heap. That's interesting.
I
Yeah,
don't
heaps
think,
are.
I don't think we did.
Yeah, heaps are definitely a thing. Heaps are useful the same way a partition is useful. Again, it's semi-sorted, kinda. No, it's not sorted at all. That's not correct. It has the property that the first element is either the biggest or the smallest in the whole group. You don't know anything about anything else. Okay, so as it mentions here, that could be a thing in a priority queue, which is a queue, except that there are people that are more special than other people, you know, kind of like a real world. So if you could pick that top one out, then that's the one you're going to use. Okay. So with the heap, you just have to keep in mind the 2 properties here. The first is the shape property. Okay. So unlike the ABL trees, although these are trees also, and these are binary trees, but they're not binary search trees necessarily. The shape property means it has to be essentially complete, which means everything's filled in except possibly the rightmost bottom level of leaves. Okay. So if you have 3, then they have to be in a, you know, in a triangle. Okay. If you add another one, it's got to be the left child all the way to the left of the left item. And then you do this one and then that one and that, you know, move to that direction. So because they don't have to be binary search trees, then you can put them wherever you want them and you can enforce this property. But the other thing is called the parental dominance or the heap property. Okay. So that says, again, it's kind of the inverse in some ways of binary search tree, or not really the inverse, but the contrapositive maybe. The key is greater than all of its children. Okay. So a binary search tree, smaller to the left, greater to the right. A heap, all children are smaller than the parent. Okay. But it doesn't say anything about the relationship of the siblings to each other. Okay.
So why on this page is the middle one not a heap?
The middle one, because it's not essentially complete. If there are only 2 leaves there, it would have to be over here.
Okay,
You can only, so like this, you can only have, if there's anything missing, you have to start with this one and then this one and then that one and then that one.
so could there be two things missing and they both be off of that 5?
Yes.
Okay,
If the one were gone on this one, then you're okay.
okay,
It just says if there are any, if it's not complete, the leaves that are missing are to the right of the bottom level.
so you have to go left to right, fill it in.
Yes.
And it's still binary, right?
It is binary, yes.
Okay.
But in fact, I said it's not necessarily a binary search tree. It really can't be a binary search tree, right? A binary search tree has to have the left child less
Yeah.
than. That would not be a heap. So these are different things, okay? So what's the point? Well, the point is that it can be quicker to put together than having to do a binary search tree from scratch, okay? And it goes through the two ways we can do this, through the bottom up and the top down. So the bottom up, you actually start with, if you're, so here's the bottom up construction of the 2, 9, 7, 6, 5, 8, okay? You just put them in order, the 2, then the 9, and then the 7, without any thought to anything, okay? So you put them in the order that they come to you in the list, okay? Making that essentially complete tree. Once you've done that, you then heapify it by going through and looking for those parental dominants, okay? So you start here, in this case, with the last node, which is the 8, and you make sure that it's okay. It's not, so you flop them, okay? And then you go over to the 9 and make sure that it has a parental dominance over its 2 children, okay? And it does, so it's okay, okay? You then move to the 2 and see if it has parental dominance over its 2 sibling or 2 children. It does not, okay? So you have to flop those around, the 9 and the 2. When you make that change, you may have upset the apple cart down here in case, in fact, that you did. So whenever there's a change, you have to recalculate the parental dominance down here and flop those back around to get you to the final form, okay? So this is a heap based on this, the input here, using the bottom up, okay? So again, the bottom up, you put everything into a tree, to a binary tree. And then you go through, starting with the last node, the last leaf node, and make sure and flip them if they're not the dominant. Okay.
So you
Does that
work
make
from
sense?
from the right backwards then.
Yes, the bottom right. Yes. And then on that level to the left, and then up from right to left all the way. Okay. And flopping those around until you get to where you want to be. Okay. The other way to do it is the top down. The top down is going to add them one at a time, always keeping them in position. Okay. Well, they talk here about insertion into a tree. Okay. So if you already have a tree, then when you go to insert something, you put it in that vacant spot, and there's only one spot that can be, right? It's going to be the bottom right of, if there's empty spots, that's where it's going to be on the bottom row. If not, you have to start a whole new level. Okay. You then go through that whole heapify procedure, making sure it's going to work itself out. Okay. But the other way to do it, and that's I thought they don't give an example of this. That's really weird. They talk about it. I guess they don't show it. The other way we don't do as often, it talks about it here, is the top down heap construction. Okay. With that, you're going to add a node. And when you add the second node, you check the dominance there. Okay, then you add the third node and check the dominance. So you're building it up as you go, rather than having an existing tree and going backwards. Okay.
It says it doesn't show an example because that's one of the exercises.
Oh, there you go.
Yeah,
Yeah,
the one
would
that
make
we
sense.
have to do. Yeah.
Yeah. So yeah, that's not the way we tend to do that. Okay, it tends to be a lot more swapping. Okay, I think because if you just with the bottom up, you just throw it all there, there's a chance some of it's going to be right. Just the odds are that a few of them are going to be okay. I think that, and you already have the structure, and you're doing less checking and checking and checking and rechecking. Okay, so that's why that tends to work. Okay, so definitely the
So-
bottom up is the way you go.
So the
But
top
top-
down, you're inserting it at the top and then pushing things down as,
Yes.
okay.
So a top down, if you had 10 elements, you'd start with a heap of one element.
Right.
And then you would have a heap of 2 elements, and you'd have to flip it around. And then you'd add the 3rd element and then flip them all around. Then add the 4th element and flip all those around. Where with the bottom up, you would always have 10 items in your heap.
Right.
It wouldn't be a heap yet. I mean, I guess that's a thing. At every point along the way, with top down, you always have a heap because you maintain it every step. With the other, you start without a heap and turn it into a heap. Okay.
David, on the homework questions, like I wasn't sure. I understand like the trees, the heaps, like I understand how to do that with them.
Right.
But I wasn't sure on the questions if we were supposed to do the trees or if they're supposed to look like they do on 232. And I don't have a clue how 232, how you get those.
232 is heap sort, which is problem 7.
Yes. Well, and it doesn't matter in either case. I mean, that's the answer there. The array is a representation of the heap, just like the tree is. Okay. And it goes where it starts with the root nodes in the first spot, and then come the next level or the next 2, and the next level are the next 2 on the array. Okay. I find that most people find it more straightforward to do it as a tree. Okay.
Okay.
So can we do number 7 as the trees instead?
Yes.
It says use the array representation, but
Oh, does it say to do
is
that?
it
Oh,
okay
it
to do
does.
it as a tree?
To really, here's what I would do. I would do it as a tree and transpose that to array form.
Okay.
Which is what's on 232, correct? The array. Notice.
232. Let me see.
If that's the case,
Yes.
I'm going to need you to go over and explain that.
Okay, so let me switch over to my iPad. I'm glad we needed it. I was all ready this time. Hate to bring a cannon on screen and not fire it. Okay, so the idea here is that there are 2 ways that you can go about doing these. Okay, so if you have the numbers, whatever they are, 5, 8, 6, 4, 3, 1. Okay, on a bottom up, you would do a 5 goes to an 8, goes to a 6, goes to a 4, goes to a 3, goes to a 1. Okay, and then you would start here checking for that dominance. Okay, but the idea is you can also put it in an array form. And I don't remember because I've killed that. Do we start at the 0th position, or do we put something? Seems like you put something special there, like something bigger than every element in the heap. Is that correct? Somebody have their notes handy?
They said to put a sentinel there or leave
Yes.
it blank.
Yes. So something. So if our biggest number is an 8, so sometimes people put like a 9 there for some weird reason, but it doesn't have to be anything in particular. But things start right here. Okay. So if in the way we number arrays, the 1 position is going to have the root. Okay. And then the next 2 positions are going to have the 8 and the 6. And then you're going to have the 4, and then the 3, and then the 1. Okay. And that's how you transpose those around. Okay. So if you're doing it in the way the book had it, you would have, the 9, 5, 8, 6, whatever. You just have those written as a list. Okay. And then the first thing you do is you check this 6 and 1. Okay. So I'm checking over here. Okay. And that's okay. That perimeter, so you don't change anything. Okay. So that would stay at the 9, 5, 8, 6, 4, 3, 1. Okay. You would then check, this one's all going to be correct. Well, not all. You would then check over here. That's okay. You check over here. That's okay. Okay. You then go and check over here. And this is not okay. Okay. So you would have to swap these. Okay. So you would swap, and they make the one that's the root we're checking with bold. So you've got the 5 is bold here. Okay. And when you see that the 6 is bigger, you would change that to a 9, 6, 8, 5, 4, 3, 1. okay? And then you would check, this is now a 6. Only if my pencil works. And this is now a 5. Okay, and this is how I would do it. I would have a scratch piece of paper with the tree while I'm filling out this other stuff, okay? You then have to check this relationship, and that's wrong too, okay? So in this case, it's the 6 on top. So that would be a 9 with the 6 in bold. 8, 5, 4, 3, 1, okay? That doesn't work, okay? So you have to switch those. So the 6 goes here, and the 8 goes here. That is ugly. There we go. So that would give you the 9, 8, 6, 5, 4, 3, 1. Oh, we don't care about the 9. I'm like, what? Where's the 9 coming from? The 9's our made up number, so we're going to skip that one. I'm like, it's not working. Okay. Now we're done, right? Now this is in a heap now, okay? And the heap sort works once you're at this point, you know, because it's a heap, this is the biggest element, okay? So you're going to move it, you're going to partition it off, and it's over here. And you're going to flop it with the 1, okay? So the 1 goes here. So it's 1, 6, 5, 4, 3, okay? And now you have to heapify this. So again, if you want to keep it straighter, it's a 1 there to a 6 to a 5 to a 4 to a 3. That's it, okay? So then you have to go through starting down here. Check this one, that's okay, okay? That is not okay, so you have to switch the 5 and the 1, okay? So that would, you would have, this would be the one we're trying to check on, okay? No, that's not correct. Oh yeah, it was a 1, but I just switched it. So the next one would be a 5, 6, 1, 4, 3, okay? And then I would have to check this one, okay? With this one being that's the wrong color. This one being in bold, that's the one that we're checking against. We would then flop that out with the 6, 5, 1, 4, 3, okay? Once we get to that point, we would then break off that 6 and swap it with the 4 and get the 4, 5, 1 and keep going down from there, okay? But you can always make a tree because I think it's just visually makes more sense, okay? But with this, basically, you're saying that this one's the root, okay? Its 2 children are here and here, okay? And then the children of 6 are going to be there and there. And is that right? I've lost something along the way. Oh, I've got this 1's in the wrong place. Yeah, I messed up the order somewhere, but you can get back and forth between the array and the tree, but I think the tree are easier to deal with. Okay, if that makes any sense. But you can always tell, and what the algorithms end up doing is you can tell from any position where its children are going to be. Okay, so if you're at position 1 with that 5 there, before we switched it all around, that's why it doesn't look like it did anymore. So let me go back to the original. That's what was confusing me. I'd modified my tree. So if you have 5 on top, you have an 8 over there, you have a 6 over here, you have a 4 over there, a 3 there, and a 1 there, okay? So the 5's at a 0 in the array, its children are at 1 and 2, okay? The children of 8 are going to be, so we have 1, 2, no, I'm sorry, it starts at 1. We start at 1, its children are 2 and 3, okay? The children of 8 then are going to be at 4 and 5. Okay. And the children of 6 are going to be at 6 and 7, if there were such a thing. Okay. And you can figure out that relationship because the computer can't do the graph. Okay. But as far as testing goes, doesn't matter to me. As long as you can turn the graph into the array, you're going to be fine. Does that make sense? Everyone's still confused.
I think I'm still lost.
Okay.
Is the, when you do the line, that's for the deletions?
The line means that it's not a deletion, it's in place. Okay.
Oh, okay.
So when we're right here, this is a heap. Okay. It's the
Right.
first time we've got a heap. When you have a heap, you know that the first element is the biggest. Okay. But we want to sort this in ascending order. So it should be at the end. So we move it to the end and we just ignore it once it's there. Okay, make sense?
When it's in place and you know it's sorted.
Not sorted, you know it's a heap.
Yeah.
So,
when
so you know
it's-
the biggest one's first. So you swap it
Yeah.
out to make it last. Okay. And then if you were to do this, if you can continue to do this, you would end up with it in reverse order at the end of each row. So the 8 would be there, the 6 would be there, there'd be a 5 on the next one, then a 4, you know, and so forth.
So you pick off the largest one, like down here, and then you
Yes.
keep sorting until you've picked off all of them.
Yes. That's the idea. Okay. So again, and you can go the other way if you have a random array of numbers. Okay. Again, we're going to put nothing in this one. We'll just mark it out. Okay. Whatever numbers we have. Okay. This represents the tree where 3 is the top one. Okay. It's at position 1. So 1, 2, 3, 4, 5. Okay. Its children are at 2 and 3 always. Okay. So that's a 7 down there. And that's a 4 down there. Okay. And then we're going to go to a 1 over here and a 2 over there. Okay. And that's at the 2, the 3, the 4, and the 5. Okay. So the array and the tree are identical. Okay. And it's not a heap yet. Okay. So again, the way heap sort works, you turn this into a heap. Okay. And you do that by going at the end here, and you just have to know what you're looking at. So you know, and there's a formula to get from which number you're on to its parent. Okay. So if you're at the 2 in this position 5, then you know that its parent must be at position 2. Okay. And if you're at position 4, its parent is also going to be at 2. Okay. So you know to check this against that and this against that for parental dominance. Okay. And they're okay. So we don't have to worry about that. Okay. So you then move up a level. Okay. So this was okay. This was okay. You now move back to the 1 and its children that are going to be at 2 and at 3. Okay. And you start with the one at 3. Okay. And this doesn't work, right? So you have to swap. We use blue for the swap color. You swap these two around. Okay. So if we're dealing with just the array part of it, then it's going to go like they would list it. We had 3, 7, 4, 1, 2. Okay. We're going to swap the 3 and the 4. So now it's going to be 4, 7, 3, 1, 2. Okay. Which would represent on the tree changing these two around. Okay. We now have to compare the new one here, which is the 4, with the 7. The 7's the biggest. So the 4 and the 7 are going to swap to give the 7, 4, 3, 1, 2. Okay. And that's not sorted. We weren't trying to sort it, but it is a heap. Okay. So again, just to make sure it's a heap, we can test ourselves here. We have 7, which goes down to a 4, which is smaller than it. So we're good. Which goes to a 3, we're good. Which goes to a 1 over here, which is smaller. So we're good. Which goes to a 2 there. Okay. So what we know now at this point is that this is the heap and that this is the biggest element of the heap. Okay. So we're done with it. We're going to send it to the end of the line. Okay. So we're going to move the 2 over here. And we could do a lot of things. I mean, it's an algorithm. You can do what you want. We could just move everything 1 to the left, but it's easiest to swap it. Okay. We swap the 2 there and we're going to make a special little room over here for the 7 because we're done messing with it. Okay. And then the 4 and the 3 and the 1 are still there. Okay. So the 7's been put in timeout or something that we're not going to mess with it. Okay. So now for all practical purposes, we have a list of 4. We then heapify that 4, those 4 numbers. Okay. And then we'll move over. So when we're done with that, okay, we can just work this example out. Okay. So the 2 will have the 4 and the 3. Okay. But the 1 is going to be under the 4. Okay. So the 1 and the 4 we check, they're okay. But the 2 and the 3 are not okay. So we would have to switch the 3, 4, 2, 1. Okay. Then the 4 and the 3 are not okay. So we have to do the 4, 3, 2, 1. Okay. We're at a heap again. Okay. So we're going to make another area here and we're going to swap the 1 over to here and put the 4 here. Okay. So then in keeping up with our tree here, we're going to have a 1, 3, 2. Okay. And unfortunately, we're going to have to start by swapping out these 2, go to a 2, 3, 1 to check that one. The 3 and the 2 are wrong. So we're going to go to a 3, 2, 1. Okay. We have a heap again. Okay. So the next thing we would do is we would swap the 1 to the front, then the 2, and then make our new line for a 3. Okay. With the 1 and the 2, they're also in the wrong position. So we only have one comparison. We go to a 2, 1. Now that's a heap. Okay. So we flop those back around to where we just were to the 1, but we're going to make this 2 out from there. And then finally we have the 1 by itself. Okay. So this sorted is starting here 1, 2, 3, 4, 7. Going backwards, right? That make more sense? Less sense?
I think what I was not understanding is, like, when you get the heap, why do you have to keep going? Like, if it's a heap already, but it's trying to sort every single one of them, right?
Yes. Yes.
Okay.
So
So I was just thinking, like, once it's a heap, why do you need to stop? Like, why do you need to keep going?
yes.
But it's because it's trying to sort of every single number
Yes.
to make sure every one of them would still be a heap no matter what happened.
Well, the bigger goal has nothing to do with heaps at all. The bigger goal is just to
It's
sort
just
the list
a
of
sort.
numbers.
Okay.
So, but by creating a heap, you're finding the biggest element. That's it.
Okay.
I mean, you could have a heap where you find the minimum element and then the parental dominance gets reversed, but we don't normally do that. We'll stick with this one. Okay. So that's all we're doing. So if you have 10 elements, you're going to find the biggest one, make it a heap, move that off. Now you've got 9 elements. Find a heap again. The biggest one will be first. You move it. Now you got 8 elements. You keep going. Okay.
So what we should do is as an array is both parts, like the construction to get it like basically bottom up into a heap.
Mhm.
And then go ahead and remove the biggest element and sort the next part into a heap.
Yes.
And continue until it's nothing.
Yes. 2 down to 1. Yes.
Okay.
One.
The last one.
Yes. Yep.
Okay, thank you.
Okay. Everybody else clear?
I think so.
One thing that Anna had asked that I dealt with on the forum, but I'll deal with it here as well. They gave you the list 1, 2, 3, 4, 5. They wanted you to sort that in ascending order, and it's already sorted, right? So why do you do that? Well, the why turns out to be a little interesting. At least I think it's a little interesting. It turns out that, well, first off, the computer doesn't know that it's sorted. It's randomly sorted, but that doesn't, we can't prove that just by looking at it. Okay. So that's the first thing. You don't know that it's sorted, even if it happens to be. The second thing is one more of theoretical interest, I would say. It's often the case that algorithms do very poorly if you give it a pre-sorted list. Okay, so you want to kind of test that. Often either a pre-sorted list that's already sorted or a reverse sorted list give you the worst cases. Okay, so you can test those things. Okay, but if I give you a list of 1, 2, 3, 4, 5, you know that it's sorted, but the computer doesn't know that it's sorted. Okay, so that's why you have to go through the process. And the process is just the same, right? You just take the 1, 2, 3, 4, 5, you turn it into a heap. When you're done with the heap, the 5 is going to be on top. Okay, you're going to pull that to the side. So don't let it confuse you if they are sorted already. It's immaterial to the problem. Okay. Again, it's that problem. It's always tricky the way we would solve a problem versus the way the computer would solve a problem. Okay, unless you specifically tell a computer these things are sorted or you want it to check that, it will not recognize. There's no recognition that a computer can do that things are sorted or not. Okay. And it's a weird example, I think, in some ways, because it will confuse people. Well, it's already there. Why do you have to do it? But that's why. Okay. Other questions about heap sort?
On the homework on that section,
Uh-huh.
so for number 1, we can use like the trees. Like that is just basically like doing the same thing they did in the example, like 186. You're just putting those into a tree and then doing
Yes.
the parental dominance.
Yes.
That's for A. And then for B, where the successive key insertions, that's what you were talking about before, where you
Yes.
do it as you go. The biggest one always goes on the top.
Yes. You put an 8 first, and then you put an 8. The 1 first, a 1 with the left child of an 8, and then swap those. And then you add the 6 and keep swapping around. Yeah, that's how you do it.
So number 7 is the one that has to have the arrays to where you
Yes.
can use the trees to kind of guide you on what to put in
Yes.
the array.
Yes. Yes.
And I think my confusion was I didn't understand where the numbers on 232 were coming from.
Mhm.
But now that you showed the trees and how you relate it back to the trees, I think it does make more sense.
Okay, good. Other questions on the heap sort?
So on the top down for question 1B,
Mhm.
When you get to the third element, that would actually be a right child, correct? And then you'd have to do
Yes.
okay.
You'd have a 1. So you'd have 1 first, right? And then the
Mhm.
1 with a left child of 8. Well, that's wrong. So you got to flip it around. So 8's your new top, 8 with a 1 to the left. It would then be 8 with 1 to the left and a 6 to the right. And that's okay. You wouldn't have to worry about anything else. Okay. And then the 5 would go off of the left child of the 1. And that is a problem. You'd have to go through and heapify
Okay.
that every time.
I just
Yeah,
wanted to make
if
sure
you do both of
I was
those,
getting the directions right.
Gotcha. If you do both of those, you'll see why we don't do the top down much. because it takes a lot more work.
And David, you always start comparing from the right child first.
When you're heapifying, yes, you add to the left, you compare from the right. And again, if you want to be perverse and just reverse your right and left on everything, it still works, but just don't flip those along the way. So pick a direction, stick with it, you're going to be fine. Okay. So the next one on Horner's rule, we skip it entirely. I mean, it's some cool stuff, but yeah, it just seems like a lot for us to deal with right now. If you teach high school math and have like advanced students want to do some cool stuff, there's some cool stuff here. No question, but it's beyond what I think we want to deal with. Okay. So Kim, if you haven't watched the video yet, you now know you can skip this whole section.
No, I figured that from the homework problems.
Okay, there you go. Okay.
So.
And then problem reduction is almost like a preview of what we're going to talk about later on. So there's not too much necessarily here for us to do. There wasn't any homework from this section, was there? I don't think there were any.
No, it was stopped at 6.4.
Yeah. So, I mean, this is an interesting approach that we're going to see later. So I just don't want you to have to spend time on it now. But it's the idea that if you can, and this is the best example, I think, of why this works, is if you want to do the least common multiple of two numbers. It turns out there's not a particularly neat way to do that. Okay. Like the GCD, we have Euclid's algorithm that's pretty efficient. We know how to do that. So rather than try to figure out something messy for the LCM, if there's a way to convert, if somebody asks for the LCM, convert it into something we do know, which is the GCD, then that's going to make our lives easier. And that's the point. So the point is, if somebody asks you for an LCM, you instead do the GCD of those two numbers and then divide the two numbers multiplied by that GCD. It gives you the LCM, and that's how you're transforming and conquer. Okay, you're transforming it to a different problem where there's a known relationship between what you're looking for and what you have. Okay. So, I mean, that was really the thing there, I think, that makes the most sense. We will later get to when we're talking about problems that have no good solutions, dynamic programming and things like that. Some of the techniques will look kind of like that. So we'll come back to that idea, or linear programming also. But yeah, we're not gonna worry about that yet. But it's ways that we can solve things like the knapsack problem, which has no known polynomial based solution. Okay. So, and this, if you're ever curious, this is the peasant, the wolf, the goat, and the cabbage problem turned into a graph problem. Okay, which may make things easier, maybe not. Okay, but yeah, we're not doing much with that. I usually make my students prove this first one here, that LCM of MN is equal to MN divided by GCD of MN, but I didn't want to do that to you.
Have we done the peasant, the wolf, and the cabbage
Did we do that
question and I just missed it?
Oh, maybe we didn't do it. It's on the cover of the book. I usually do it, but I try to give you guys less homework since I know you guys have lives, unlike my students who may have lives, but I don't care about their lives. I care more about your lives than I do about their lives. That's not correct, but you get the idea.
Well, they're full-time students, right?
Yes. Now, some of them work full-time too, but I can't help that. That's an unfortunate aspect of their life, but yeah. But yeah, that's just, I mean, you've seen similar problems of, well, we did one with the soldiers and the ferrying the soldiers. It's the same kind of an issue. You have artificial restrictions on the free flow of people, and you got to figure out the way to do it. So. Okay.
Can I ask about the one in 6.1 about the student records?
Yes.
5B.
6.1.
It's on page 206.
Yeah. Yep. Which
So,
one? 5.
The 5B.
Yes.
Yeah. So if we have to design the algorithm,
Yes.
which is my least favorite thing to do, I'd rather solve the problems all day long than
Yep.
to
I agree.
design an algorithm for it. You're basically like using the address part if you're looking for like which are the states they're from.
hmm
Is that you're sorting them by state?
Well, you have options here, but you're struggling because no way you sort is going to make any difference. That's why you're struggling, right? You could
Yeah.
sort by the state they're from. You could sort by their first name. You could sort by their last name. None of that helps you solve the problem. Okay. So in that case, it doesn't say that you have to do a sorting algorithm. Okay. If sorting does no good, how would you just solve this problem if you didn't have to sort?
Look through every single one.
Algorithmically.
Brute force.
Yeah. Well, it's kind of brute force. Yeah. I mean, I think for record keeping, so when you say go through each one, that's correct. And that's brute force. But how are you going to keep track of each state? Well, you could have a counter for each state or an array that has the 50 states, in order or whatever. And then whenever you see that state, you add 1 to that counter. That's the basic way to solve it. So sorting has nothing to do with it because there's nothing you can sort on that would help you any, right? And again,
Unless the state was in its own field, which
Even- it
it
still
probably
wouldn't matter.
wouldn't be.
and it still wouldn't
Oh,
matter
okay.
because, I mean, you could sort it, but again, this is going to be a linear problem, right? No matter how you keep track of it, you're going to have to go through one time for every student. There's nothing you can do to magically not have to touch every student's records. So it's linear, okay?
Mhm.
To sort it is going to always be worse because it's going to be an n log n instead of an n.
Right.
So when you see that there's a linear solution to this, you don't have to even worry about sorting. You can say that. You can say there's a linear solution. Here it is. You go through and when you see Alabama, you take off Alabama. You see Alaska, you take off Alaska.
Mhm.
You read each one once. You're done. That's more efficient than anything sorting because the sorting would be n log n before you start anything. And again, I think this one is good intuitively because what are you going to sort on that would even make it any difference? This one doesn't even feel like
Because
sorting.
then you'd still have to count them.
Yeah, you have to touch every record once and just
Mhm.
once. So it's linear all the way. Does that make sense, Christina? I know, Christina, you've had problems with the efficiency. Does that one make sense? That if you've got however many, you've got n students and you want to find out how many are from each state, you have to read through each student's records.
Yeah.
And
It
that
does.
tells you you're done. So it's n times, that's big O of n, right? That's linear.
I think
Okay.
my issues get into when it's like the dividing ones.
Right.
I
The
I think
logs,
that's,
log ones.
yeah, the brute force ones that are like pretty straightforward, even the
Mm-hmm.
like n squared and cubed. I mean, I can see
Gotcha.
those. I think it's some of the other ones.
The
that-
log ones are the weird ones, no doubt. Yep.
See, I had originally thought on that one, you sort them and then you count how many are like Virginia. But I guess
That's
in
more-
that
yeah, it's more
particular
work.
case, you're still having to count each one of them.
Yes. Yes. Yep. Yeah. I mean, again, the search can be so efficient because if you find what you're looking for, you don't care about all the records, right? There can be 1,000 items in the database. If you find the one that you want, you're done. And you can ignore all those. So that allows you to get less than linear, okay? But if every piece of data has to be looked at least once, then you're at best linear, right? Because you have to look at every piece of data. There's no magical way to make that go away. Okay. I think we'll get to that chapter where we talk about, you can look at the theoretical efficiency of any process. Okay, so you can find out without even looking at any algorithm, just based on how much information that you have to touch, what the best algorithm could be. So you may have algorithms
So
that are
you
worse than that. Go ahead.
You wouldn't even necessarily need to have all the states there already, like for it to sort into, it would just be like when it found a new one. And then every time it sees, it would count another. Like,
You
so
could-
if, if the first 10 are Virginia, it
Right.
would just add to Virginia, and then the next one's Tennessee, well, it'd have to add a new entry.
See,
And
I
then
think
like if the next
adding-
one,
yeah, but I think adding the new entry is going to be more of a hassle than just adding them all up front. Because then you've got two paths through. And then you have to find out, is this a state I've seen it on before or not? Because they're not sorted. So you'd have to search every time. Okay, we have a Virginia. Okay, we'll add a Virginia. We have another Virginia. Good. We have a Tennessee. Have we seen Tennessee? You don't know that. You'd have to go back and search to see if you'd seen Tennessee and then add it. That's more work than you need. So that's why pre-populating all the states with their own counters is going to be easier. It's going to make the algorithm simpler.
David, on that one for the pseudocode, I mean, can you literally just say like set state counters to 0 and
Yep.
then scan and increment?
Yep. Scan
Okay.
scan each record and find the state that they're from, increment that state's counter. That's the algorithm.
so you
Okay.
could say like array is the 50 states.
You could,
Okay.
in alphabetical order, and you don't even have to know what that alphabetical order is. Doesn't matter. So. Other questions about that one or anything else? Well, okay. I actually managed to record this time, so I'll go ahead and put the recording up. And then expect either Saturday or Sunday to be a review video. Will not be any homework for this week, but the test will go live on Friday. You'll have Friday till Sunday. Again, I'll make it a 1 hour exam, but I'll give you 2 hours to take it. And depending on when you take it, you can try to message me. And if I'm awake and aware of the world and not in class, I won't mind to answer, but you're taking a chance on when you take the exam. If it's 3 a.m., not going to be awake. If it's 10 p.m., there's a fair chance I'm not going to be awake. If it's 5 a.m., I very well may be awake. So anyway, take your chances on that. Okay.
David, just out of curiosity, do you have any idea about how many questions an hour might be?
I would like there to be 10 because that's a good round number, but that may be a lot. I really have to look at the complexity of the numbers, of the questions, because some of these are real simple, but if I put a Gaussian elimination, that's worth at least 3 other questions. So
Yeah, I'm just trying to think of like which ones do I think are going to take me the longest?
yes. And I'll try to figure that out. And I've taught this class a lot, so I have a rough idea. I'm teaching a couple of courses this semester I haven't taught before, and the testing's really hard because I don't really know how long it takes students to do this. You teach stuff a while, you get a range in your head, but when it's new, you have no idea. So one test, nobody finished. One test, people were done in 20 minutes. So you reevaluate and you figure it out next time. But yeah. About 10 problems, but that's probably too many.
Okay. So no more than 10.
No, I wouldn't. I'm not going to say that. So you can hold me to it, but no, I can't imagine. I mean, at 10 problems, that's 6 minutes a problem, basically.
That's awful fast.
There's not a lot of problems we've done that you can do in 6 minutes. So
Especially if they're algorithms.
yes.
I've been killing myself with the algorithms.
Yeah, they're horrible. Yeah, I know. I understand.
So you're thinking about the problems being more algorithm based, not just like knowing what certain thing, like I don't say vocabulary, but you know what I mean, like
right, the concepts. I mean, the class is algorithms, so there's going to be some algorithms on there.
Okay.
I will try to make them quick and relatively straightforward, just because, doing an algorithm is a creative process. You can't just do it off the top of your head sometimes. So
we were talking about the class a little bit on our like Facebook group. And one of the things that I kind of finally came to the conclusion is the thing about the algorithms and like doing the pseudocode that I think is frustrating is because we've, at least for me, is because we've already had 2 different programming languages.
Right.
I want to write the program and test it and see if it works.
Yep.
And with pseudocode, you're not really doing that. And it just feels really imprecise.
Yes.
So I almost was like, maybe in the future, I don't know if they wanted to like, because I know you guys are going to start over again
Yep.
with new people and whatever this summer.
Yep.
Is like in the future doing the programming classes last. So basically switching the, I don't know if that would be better. I mean, you know better
Yeah.
than us, but
I mean,
I
no
don't know,
one
that
does
just-
that, which doesn't, that's not an answer. That's not a defense that why we don't, but computer science programs do not ever do that for whatever reason. We can certainly think about that. I mean, I'm open for any suggestions.
I don't know. I
about
guess
that,
that's just I don't know if that's just my mindset or what, but I think that's what's frustrating is I feel like, well, I guess this works. I don't know.
Well, I think what's frustrating, and this is always frustrating. I mean, you guys teach math, you know, we're moving from doing it to the theory behind why we're doing it. And that's always harder,
Yeah.
you know, but at the same time, which do you do first? Do you talk about how you do it and then you do it? Well, I don't know, but that's what we're facing. But this is, the algorithms are harder because they're the theoretical construct that we make programs out of. That's why they're hard.
Mhm.
And you can test them, but only with your pen and pencil and paper in your brain. It doesn't automatically test them. So
I think the hard part of the pseudocode is not really knowing like if you've done enough,
right.
like does it look right? Have I said enough or is it too, I think it's
Yes.
just that balance of there's really no way of knowing if it's right or wrong.
Well, no, I mean, the way to do it, you have to work through it. That's when I grade your papers. That's what I have to do. I have to look, okay, let's take a real example using your algorithm, go through and see if every step says what it's supposed to do, we're good. But if it leaves you somewhere else, then it's not good. So
Well,
you can't test
if you
them.
followed the pseudocode for my, like, I forget which one it was, problem set 2 with the coins, then kudos to you because I was like,
I tried it with coins. I lost a lot of money. It was weird. They just disappeared. And some of them burst into flames. It was the weirdest thing.
I just could not get, like, I was trying to like get it, like it was like all these different scenarios and I kept getting myself confused. And so I was like, he's gonna look at this and go, looks like she worked really hard.
Yeah.
Cool.
Yes.
I mean,
and that's okay.
A
But
for
it's a
effort.
new language. It's a new language, so it takes a while, right? I mean, we're not used to speaking this way. This is how mathematicians talk, and they're weird. You guys know some mathematicians, I assume. They're all weird people. So, yeah, so you're learning that language, so it makes it hard. Okay, so I think we talked enough about this stuff. So, again, videos coming out Saturday or Sunday. If you have questions anywhere along the way, just send me a message or whatever, and we'll try to work it out.
Are we gonna have office hours next week?
Yes.
Just
Yeah, that'll be right before the exam goes live for last minute questions. Okay.
All right.
Okie dokie.
Thank you.
See you guys later. Have a good week.
thank you.
Thank you.